Okay, thanks for the introduction. And I'm Shih-Chun from NTU Taiwan. And this is a joint work with the Professor Shih-Chun Huang at the Purdue, USA. And Professor Yishan Wang, who is the chair of the IT Society Taipei. And Professor Yiqu Huang, who will also give a talk tomorrow. And my student, Yishan Liu. So indeed, we know that in the 5G, there's a new use cases called ultra reliable and low latency communications, URLC. And the URLC is a very hard use cases because we want the low latency. So in terms of channel coding, the broadness cannot be very long. So typically, it should be less than 1,000. So typically, only 100 symbols. But the reliability must be high. Sometimes it's 10 to minus 5 to 10 to minus 6. So it's a very hard technique. And the low latency means that the brightness is very short and also a high reliability. But currently, although 5G has already studied these URLC use cases, typically people just use a very high transmit power, or many frequency band to increase the reliability at a low latency. So if we really think about the throughput, the current solution is not a good solution. So as proposed in the JSX editor last year, so if we consider high throughput, not all future KPI in the 6G cannot be met for the current 5G URLC. So it motivates, we need to consider a new network information theory. We need to study the optimal trade-off between the rate, broadness, and error probability. So in this talk, we will focus on a simple model. It's called a broadcast packet erasure channel. So now there's a common transmitter who want to send two primary messages to the receivers. And the channel stack is a link erasure. So the Z1T and the Z2T, it means that if the Z1T is 1, and this user receive the packets. If the Z2T is 0, then this user have an erasure. And for the mathematical to trace the result, we model the link erasure as a ballooning process. And many practical West network coding has been motivated by the capacity result of this broadcast packet erasure channel, PEC. So for this channel, let's see how if we can study the trade-off between the broadness and the error probability and the rate. So one very promising result is that if the two receivers can provide feedback with a causal feedback, and here with the feedback we sometimes call the causal CSI feedback because it's feedback the erasure state of the channel. And if there's no broadness constraint, this feedback is very useful. It says that there's a no feedback capacity region, and this is the feedback capacity region. We can find the feedback capacity region, and it is strictly larger than no feedback. So because in many bouquet channels, the feedback cannot enlarge the capacity region. So this is a very exciting result, is that feedback indeed can help. So this is a result from the Georgitas and the Wang. But now the problem is that if we doesn't let the broadness go to infinity as a classical Shannon limit, and one of the classical measure is the channel dispersion, then can we do this finite length analysis? But indeed, if we consider this broadness, then the analysis is very hard. So the dispersions with two primary messages is very hard. Typically, people consider at least one common message. For example, this paper, this TIT-80 paper, consider there's only one common message. Or the other paper from 10 is that consider degraded message set. Is that also there is a common message. So why this is hard? The problem maybe comes from the find the converse, match converse. Indeed, for the even for the two-user channel with private message under the finite broadband is very hard. Okay, so this is a main point. How to find tight converse, which is the focus of my talk. So because consider the journal coding may be too hard, especially for the finding a tight converse. So we make progress consider the linear network coding. Is that the encoder must be a linear code. Okay, if we also linear network coding is easy to implement in practice. So if we add this linear network coding, then we can find a match converse, even the broadness is not go to infinity. Okay, so this is the main focus of our talk. So indeed, we find the exact finite length LNC linear network coding feedback capacity under the two-user broadcast PEC. The exact means that our converse is tight for any broadness T. So this is our previous ISS paper. We find not so good converse, but now we can show that this converse already matched the attributability in this blue curve. Okay, so this is the focus of this talk. And based on this matched converse, this is for arbitrary T. We can also find the second order dispersion. Okay, so so this is what I will discuss in the next few slides. And for the engineering part is that we show that a simple three-phase LNC is optimal for all linear network coding. So it's better than the simple routing. As you can see, for all the finite lengths, the total sum rate is much higher. So this attributability is quite simple from the network coding view is that now we have a three-phase. So for the first phase, we only deliver the bits need to send for the user one. And for the second phase, we deliver the bits for user two. Okay, so the first two phases is just a very simple TTMA. There's nothing different from the routing. But at the third phase is that we can recycle some overhead bits. What is the overhead bits is that, for example, in the first phase, some bits will be originally for the first phase, all the bits must be targeted for the user one. But if the user one's link is off, user two's link is on, then this bit is overheard at user two. Okay, so again, for the phase two, some bits, all the bits should be sent to the user two. But will some bits be sent over her user in the user one? Okay, if a user two is off, user one is on. And these two bits can be recycled, resent at the phase three. Okay, why? It's because, as you can see, although we send the SOR of these two bits, but receiver one already overheard this B2 in here, in phase two. So he can cancel out this interference and got what you want. Also, receiver two has already overheard the interference B1. So he can cancel out the interference and get what B2, receiver two want. So it means that we can simultaneously send two bits, but only use one symbol. Okay, so the feedback has this again to increase the rate. And it turns out this scheme is optimal. Okay, so here I briefly overview what is the finite length analysis of this three-phase LNC. So if the total time, so the first two phases is that we must send the bits for at least one receiver is received. So either the bits is received for the target user one or is overheard for the receiver two. Okay, so for the second phase is also the same. And for the third phase, and we recycle the SOR. So assume the three phase has a length T1, T2, and T3, and the overall brightness constraint is T. So the successful event is that the T1 plus T2 and plus T3 is less than T. Okay, so and because assume that each link is ion Bernoulli P, then we can calculate the length of the T2 and the T1 plus T3. So let's focus on the T2. T2 is just because any of the two receiver, anyone is on, then we think there's a deliver. Okay, so the T2 is a sum of the geometric random variables, and this is a success probability because any two is on, then we think it is a correct delivery. And for the T1 plus T3, and the T1 plus T3 is a sum of IID geometric random variable with a success probability P. Is that if we look at this bit B1, so this irrational probability is 1 minus P, or the successful probability is P. So the B1 must be delivered. If it is not delivered in phase 1, it will finally deliver in phase 3. Okay, so the total length of T1 plus T3 will be all the bits here is finally delivered to receiver 1. So it's a geometric random variables with a successful probability P. Okay, so with this analysis, we can find the condition. The condition is that given a finite broad length T, whether the this three-phase LNC will have a successful delivery. Okay, to calculate error probability. Okay, and you follow this one, you can do some second-order analysis to find the dispersion for only this three-phase LNC. But the problem is for the converse, is that for other LNCs, can they have a better error probability? This one we want to care. But the problem is that typically when the broad length go to infinity, people use the degraded trick. Is that we form a degraded broadcast channel, which gives receiver 2 resection to receiver 1. We can enhance the receiver 1's link on enhance the probability that receiver 1's link is on, or reduce the receiver 1's irrational probability. And with this degraded trick, and the next trick is that under this degraded broadcast channel, when the broad length is goes to infinity, we can prove that feedback doesn't help. So the TTMA or routing is optimal. So this is the trick. But we don't know that if for finite T, whether even for a degraded channel, degraded broadcast channel, whether TTMA is optimal. We even don't know that. Okay. So this is a problem is that why the converse is so hard for this broadcast channel. So here we instead use some technique tailored for the LNC because it's linear, so we can observe the random rank enough to ensure decodability at each receiver. As long as we can find the correct subspace and the monitor its rank, if you can identify the correct subspace, and this correct subspace can ensure the decodability, and then we can bound the error probability for all possible neural network coding. Okay, so this is a simple single user example. Okay, if we only have one users, then each time, so this S1T, you can see that is the span of the received coding vector. We know that the linear network coding is a message multiplied a coding vector. So each one, if you receive a new coding vector, the receiver, the span of the receiver observation space will increase. Okay, so as long as this receiver subspace is larger enough to cover all the user's messages subspace, then the decoder will be correct. Yeah, all the message can be decoded. So if we use this subspace viewpoint, and it's very easy to prove that in this single user example that the ARQ will be optimal. It's because every time you want to increase the rank of this observation space, so you will send a new, we call a type 1 vector, which is not in the old observation space. You want to find something new, such that every time, as long as the receiver receive this coded vector, it will increase its rank. So this is what ARQ do, is that you will always send new coded vector. Okay, so this is a simple example, is that if for the single user, the subspace is quite easy to identify. But now we have two receivers, and these two receivers, the interference, some bits good for user 1 is the interference for user 2. So how to monitor the correct subspace? Okay, so we use something motivated from the mutual information. Okay, so the mutual information is that for the original receiver 1, we want the user 1's message, and this is user 1's received sequence. Okay, we want its mutual information is larger than number of the bits of user 1, and we also use L1. So we can think that this tells us the observation space, and this is the message space of user 1. Then the observation space should cover the user 1 space, and this T should be the end of the transmission, should be the big T. The rank should equal to L1. Okay, so this is we transfer the original mutual information constraint to a linear subspace constraint. But just this linear subspace is not enough. So we go back to this degraded trick. This degraded trick is that we want to find another subspace. So the degraded trick tells us we can give the receiver 2's resections to receiver 1. So here we give the receiver 2's resection S2 as long as the message of the W2 to the receiver 1. We enhance this receiver. Okay, this is what in the degraded trick, if the broadband go to infinity, what they do. And if after this enhancement, we can think that we have another virtual receiver. This virtual receiver has more observations than the original receiver. Original receiver only have a S1, its own receive sequence. But now there's a virtual receiver who can observe S1 and S2, even the user 2's message. So this virtual receiver will be stronger than original receiver. So we can think that as long as the original receiver can decode L1 messages for user 1, this virtual receiver 1 also can decode the L1 message of user 1. So it means that this mutual information should also be larger than L1. Okay, so we can find another subspace is that this is user 1's observation subspace. This is user 2's observation subspace. This is the message subspace of user 2. And all of them, if we combine them together, the rank should cover L2 bits of user 2 and L1 bits of user 1. Okay, this L2 bits is because this virtual receiver get user 2's L2 bits. So the rank will be L2 plus L1. Okay, so we have another decodability constraint. Okay, so our idea is that now we have a two receiver. We have a two original receiver. This has a two decoding constraint. And we also use add the two virtual receiver. They also have a two decoding constraint. So we have 4 receivers, and we want to modify these 4 receivers rank. So we have 4 random ranks from the 4, including the virtual receivers to monitor. So to monitor the rank, how we want to trace the time evolution of this rank vector. There are 4 elements. So this rank vector initials, all users doesn't have any observations. So initial will be, the rank will be also 0, 0, 0, 0, all 0 vector. And now if we want at the end of the broadens T, if we can success, then we can prove that the first two rank corresponding to user one should be L1 and L1. All the two virtual receivers should decode the L1 bits for the here and here. These two should all decode L1 bits of the user one. And these two should also decode all the L2 bits of the user two. Okay, so, and we want to trace this rank evolution from this rank evolution is controlled by the coding types, is the LNC coding type we transmitted. And also the erasure state. If for example, if this S1 is erased, then the rank of this receiver one will not increase. Okay, so naturally we will have a Markov decision process for study this converse. So for this MDP, the Markov decision process, the random rank vector of T is the state, and the state transition is from the action is the coding type we transmit. Okay, and also the current erasure, whether the rank will increase or not depends on the current erasure. And through the feedback, the transmitter knows the erasure of the previous time, so it can determine the next action or the next coding type, try to increase the rank vector. Okay, and we want to find the minimize error probability such that we want, in other words, we want to increase the successful probabilities that at the end of the transmission, R of T should equal to L1, L1, L2, and 2, such that the decoder will be success. Okay, and we can prove that this error probability of this MDP equals to the error probability of the LNC. Okay, so our converse match the achievability. So the three-phase LNC is optimal for all LNCs, even in the finite broadens. Okay, so this is our idea. And based on this, we can find the LNC dispersion is something like this. It's very complicated, but this is something like a dispersion term. Okay, and this dispersion, the T is a finite broadness constraint, and the epsilon is an error constraint, error probability constraint. And the next, finally, I spent a few slides to talk about extension to a vector LNC. Okay, so this vector LNC is that now the channel input is n times 1 simple vector. And so each UT1 is a coded symbol. As you can see, is that this UTN, for example, this UT1 is this is user one's message and user's message encoded by a one coding vector, and the other UT2 will be user one's message and the user two's message encoded by another coding vector. At the same time T, we can send n symbol. Okay, and these n symbols is simultaneously erased and received at each Rx. For example, in this example, all the three symbols are received at user one, but erased at user two. Okay, this is a model we consider. So as you can see, this is, of course, this is an extension of the previous, we call the scalar LNC to a vector LNC. The scalar LNC is a special case when it's n equal to 1. Okay, but why we study this vector LNC? We can prove that this vector LNC is a middle ground between the scalar LNC here and the general nonlinear network coding. Okay, so this is why we study this one. So we can somehow prove that if we replace the error event by we call a mutual information outage event, is that because for the nonlinear network coding, each time the mutual information, indeed the mutual information for user one is what I write here. The mutual information should be increased. Okay, so we can find that this if the mutual information at the end of the transmission still cannot guarantee we can decode L1 users bits, then there's a mutual information outage. This we we replace the error event to the mutual memory outage. And we can prove that the growth of a random mutual memory vector of any nonlinear code is within a complex polytope. And this complex polytope can be approximated by growth of vector LNC when the n is large. So it means that if we can transmit a lot of symbol, even you use the LNC, we can approximate the growth region of the nonlinear codes. So this is why we say that the vector LNC is a middle ground between the scalar LNC and the general nonlinear network coding. Okay, and we also prove that if user one only have a 1 bit to transmit or 1 packet to transmit, and the broadcast packet ratio channel is degraded, then the three-phase LNC, if we directly extend to the vector case, is optimal. It's still optimal for all vector LNC. So this is what we have from our MDP for the vector LNC. Is the one with circle is the tunability, and the other is the converse, and they have a match. And this is a degraded channel. Is that when the user 2 is on, user 1 is always on. Okay, this is a degraded channel, and we have 5 symbols transmit at every time. Okay, and this is our numerical result, also matches our proof. So our conclusion is that we have a matched finite length LNC converse and tunability for the broadcast packet ratio channel with 2 private messages. The main point is that our converse is obtained without the degradedness arguments, and we use a linear space-based framework. We monitor the random rank, and the random rank only have a 4 random rank to monitor, and we can trace the evolution of this random rank using the NDP, and use NDP can find the converse. Okay, and also we have an extension to vector LNCs. Is provide insights for if we want to find a converse for the general nonlinear code. Okay, so this ends my talk. Yeah, thanks.
Well, thanks, Professor Lin, for the wonderful talk. So, any questions from our audience? Any questions from our audience?
Yeah, thank you for the great talk. So I have a question. So how does this result generalize to the setting where the feedback has some delay to it?
Oh, so currently is that our delay is causal feedback. So at the time t, so it only knows the erasure at the time t minus 1. So the delay is already included.
So that delay is what? So
yeah.
Would this scheme also generalize to the case where the delay is longer than what the way you get only the channel state and 5 like concept here?
Yeah. So one thing is that is the delay is you can say waste some small symbols, wait for the delay comes to here, but you will waste some rate. Yeah, and we also have the other model is that we cannot always have the feedback. Sometimes we have a feedback, that sometimes we don't have a feedback. But to trace this model, we still assume the feedback is erased according to some Bernoulli process. So it sometimes still models your delay, but the delay is random. Yeah. Yeah. So this depends on whether we can get a closed form. Yeah. Yeah. But we haven't considered the ones that the delay is not random but always fixed, and you don't have enough time to store all the queue is not the queue story, the feedback is not long enough. We doesn't consider that case.